Hello friends, once again welcome to Passion Tronic, my YouTube channel. Friends, we have been studying basic circuit analysis. In previous lecture, we have studied Ohm's law. Today, we will study Kirchhoff's laws. Kirchhoff's laws are more comprehensive than Ohm's law. They can readily be applied for simplifying the circuit or for circuit analysis. Let us move to that. Kirchhoff's laws are more comprehensive, just as I said, and these are actually basic tools to start circuit analysis. That is, you can use them for solving electrical networks. Kirchhoff's laws are two in number. The Kirchhoff's current law, it is also called as Kirchhoff's point law, and the second one is the Kirchhoff's voltage law or Kirchhoff's loops law. As you can see on this slide, Kirchhoff's current law. See that what it states about a circuit. The statement of Kirchhoff's current law is like this. In any electric network, the algebraic sum of currents meeting at a point or junction is 0. In any electrical network, if there is a junction, what is junction? That means at a point, if there are 3 or more conductors meeting, when 3 or more conductors meet together at a point, that point is called the junction. And this statement, this Kirchhoff's current law, is about that junction. What he says, in any electrical network, the algebraic sum of currents meeting at a point is 0. Algebraic sum means consider that terms, the currents along with their sign. Algebraic sum means considering the sign while adding and subtracting and all that. And it is true that it is based on conservation of charge, law of conservation of charge. If we consider any isolated body, independent body, then its net charge, total charge, remains constant. Okay, and therefore if a conductor is used for carrying the current, whatever charge comes in, that is given out. There is no accumulation of charge, there is no storage of charge, and that's why, as there is no accumulation of charge, incoming charge is equal to outgoing charge. That means when some current passes through a conductor, there is no change in its net charge, right? So whatever charge comes to the point, the total charge is given out, and therefore when charge moves, we get the current, and that's why you can say that incoming current is equal to outgoing current. So in this diagram, you can see that see, this is one conductor for and current to that is say I1, in current through that second conductor, that is I2, third conductor, current through that third conductor is I3, and current is leaving now the junction, that is I4, other conductor. The current is leaving the junction, other conductor, and we have given the name them as I4 and I5. So at a junction, there can be incoming current, approaching current, and there can be outgoing current or leaving the junction. So according to this the law of conservation of charge, incoming current is equal to outgoing current. Now see, I have taken approaching currents with positive signs on left hand side and the leaving current on right hand side, and if I bring all these terms together on left hand side, see how it looks: I1 plus I2 plus I3 minus I4 minus I5, right? And these things, that is So here I1 plus I2 plus I3 minus I4 minus I5, and when I add them in mathematics, we can write it as a algebraic summation of all currents about a junction is equal to 0. Now algebraic summation means considering their sign, and how to assume their sign, that is a sign convention. So while writing expression using Kirchhoff's current law for a given junction of a circuit, the incoming currents should be taken with positive sign, and outgoing current, that is current leaving the junction, should be taken with negative sign. So if you consider this sign convention, you can write expression for the junction, and once you get some algebraic expression, it can be used for analysis in the sense you can find out the value of any component which is not known. So let us consider that is Kirchhoff's voltage law. So this particular law is about mesh in the sense when you have closed path in a circuit. So look at the circuit here. This circuit is I have drawn, it has a closed path. That means look at this, A, B, C, D and A. That means if you start from any particular point, you could reach to the same point going down through the complete loop, closed path of the circuit. And this Kirchhoff's current law states about that in any closed path of circuit, the algebraic sum of IR drops for each component plus algebraic sum of all EMFs is equal to 0. So actually this law is about the voltage drops and voltage difference between different points in a closed path. So when a charge moves from one point, and if it is coming to the same point, there is no change in its energy, there is no potential difference, and that is a 0. That's why as it moves through resistor, there is a fall in voltage, and of course it depends upon the direction of the current. So let us consider this particular loop. Here you can write the loop expression. Let us see loop equation for loop A, B, C, D, A. That means we are starting from point A, then going through B, C, D and back to A. So as you go from point A to point B, there is a component R1, and we have assumed the current through that is I1, and see that drop across, that is IR drop across, this will be IR, potential difference will be the IR, and therefore the first term I have taken here is I1 R1 for part AB. Then from B to C we have R2, and the current through that is I2, and therefore that component will be, potential difference will be I2 R2. As you come here, you will find that there is a source, EMF source E2, and as you are tracing the circuit in clockwise direction, you are going from positive terminal to negative terminal. You are going from that means this is EMF. As you go from positive terminal to negative terminal, there is fall in potential, and fall in potential should be taken with negative sign. We shall see it later, sign convention, and that's why this term. Then from C to D we have R3 and I3, so that I have taken here I3 R3, and then we are going to A now, from D to A. So from D to A you will find first source of EMF E1, and you are going from negative terminal to positive terminal, and there is a rise in potential, therefore it should be taken with plus sign. And then we have the last component, that is R4, and current flowing through that is say I4, and therefore that should be taken like this. So you bring all the IR terms together. IR are nothing but the potential difference across all the resistors. We have taken them with certain sign, minus, sometimes minus, plus, minus, minus. So all these are nothing but algebraic summation of IR product, potential difference, plus this minus C2 and plus E1 is the algebraic summation of EMFs, and that is equal to 0. So you can write loop equation and see that in the loop we have 4 junctions we have taken, A, B, C, D, A, and that junction, that means there can be some currents incoming, some currents outgoing. Doesn't matter, you just follow this scheme how to write the loop equation, and once you get the loop equation you can use it for circuit analysis. Let us consider the next slide. Here we are going to discuss now sign conventions. That means while taking algebraic summation of IR drops and EMFs, how to take their signs. Should we take positive sign or should we take negative sign? And for that we have convention. So let us consider for IR drop. IR drop means actually the current flows through the resistance. The current is actually the sources of EMF, and that's why there is a change in potential across the resistor. The difference in potential, PD, we call in short it as a potential difference, PD, and that is IR drop. For IR drop, look at the circuit, and I'm stating that convention. While moving around the loop, if we are going in the same direction as that of currents, then that particular IR drop should be taken with negative sign. Come to the loop, from this point A to B there is a R1 and current flowing to this I1 is I1, and our path of circuit tracing is like this. And now as you go across this R1, your direction of tracing is same as that of this I1, and therefore that corresponding drop should be taken with negative sign. Remember, if direction of tracing is same as that of direction of the current through component, that particular IR should be taken with minus sign, because current flows from high level to low level, high potential to low potential, and there is a fall in potential, and fall in potential should be taken with minus sign. That is a convention. But sometimes your tracing direction may be opposite to that, and therefore you see second point, if we are going in the direction opposite to that of currents, then take that IR drop with positive sign. Look at this particular point, from B to this source our direction is downward, and the current flowing to that R2 component is upward. That means you are going in a direction opposite to that of I2, therefore that corresponding I2 R2 should be taken with positive sign. See here in the loop expression, I have taken I1 R1 with minus sign, and for I2 R2 I have taken with plus sign. The same is the case for all the component. Okay, here also for I3 R3, see my direction of tracing is from C to D, and this direction is same as that of current of I3, it is same, therefore you have taken here with minus sign. And the last resistance is R4, the current direction is like this, our tracing direction is same, and therefore I4 R4 should be taken with minus sign. Okay, in order to explain this, illustrate this, you can see this simple diagram. We have one resistor here, and this is the direction of the current flowing to that resistor, and suppose that you are tracing in this direction. So if we are going from A to B, take IR with negative sign. In this picture you can see that this path of tracing is same as that of the current, therefore take that IR with minus sign. In second diagram, you see here the direction of the current is like this, and you happens to move in this way. The direction of this is opposite to the direction of the current, and therefore that IR should be taken with positive sign. Okay, so these are the sign convention for IR drop. So let us consider the next slide, and here you can see sign convention for EMF. EMF के लिए साइन कैसे लेना है वो कन्वेंशन. When you are going around a loop and when you are going from negative terminal to positive terminal of the source, negative terminal से positive terminal जा रहे हैं तो there is a rise in potential and therefore that should be taken with positive sign. And when we go from positive terminal like here, positive to negative terminal, then it should be taken with negative sign. And remember that this sign of sources is independent of direction of current. करंट की दिशा कोई भी हो, अपवर्ड हो, डाउनवर्ड हो, लेफ्ट हो, राइट हो, doesn't matter. For EMF, the sign of EMF doesn't depend upon the direction of the current. The convention is only thing is that when you are going from negative to positive, take it with plus sign, and when you are going from positive to negative, take it with minus sign. And once you follow these conventions, you can write such an expression using Kirchhoff's voltage law. And what is that? Algebraic summation of IR plus algebraic summation of EMFs for a closed path of any circuit or a loop, it is equal to 0. And once you get this expression, it can be easily used for simplifying any complicated networks. So this is all about Kirchhoff's current law and voltage law. I hope you have understood, and by studying these laws, your understanding about the circuit will improve. So it is time to stop here. Love you all. Bye.